Okay, so I am Piju Sher, doing PhD at IIT Madras at the Department of Applied Mechanics. So, as a part of, like, I'm the TA of this course, where I will take the uh, 1 hour live session in each week. It will be Saturday this time, that is 3 p.m. to 4 p.m. If you have any doubts regarding the course, and if you have any uh, doubts in some concepts or any problems which you are facing while solving the assignments and all, that you can ask me in this forum. I will try to solve those questions, and I will definitely uh, try to clear your doubts as well. So uh, I think all of you have already gone through that the week 1 all the lectures, right? So it talks about the uh, like the different phases, solid, fluid, and gases, and then why the fluid mechanics is of particular importance, and then professor taught that uh, the continuum hypothesis and its validity. So when the continuum hypothesis is valid, and he explained that by plotting the density versus volume plot, and showed that where the continuum hypothesis is valid. And then he talked about the fluid statics, and then he derived the momentum equations and the continuity equations. So that is what you have gone through in this week's lecture. So if you have any doubts in the first place regarding the lecture, you can ask me right now. I'll try to answer that, or else I'll just give you a separate perspective where you can derive all those equations, like the continuity equation, uh, momentum conservation equation, and as well the energy conservation equation, which you don't need in this course, but still you can do that through the formulation which I will show. So as far as the lectures are concerned, if you have any doubts at any point, you can ask me right now, and then I will try to give a different pictures of how you can derive the continuity equation, momentum equation, all these things from a integral perspective. Okay, sir took, like in the class, if you gone through the lecture, he talked about a control volume, and then calculated the different uh, fluxes through each surfaces, and then use the conservation principle to derive whether it's mass conservation or momentum conservation. But here you can use a different picture, which is the, like, what is popularly known as the Reynolds transport theorem, where you can correlate between the system and the control volume. That I will do. But before that, if you have any question, you can ask uh, for this week's lecture. Okay, no problem. Then I will go ahead with the derivation. Okay, I'll just try to do it as simple as possible. So what I'm interested to do today is so it will help further to understand the subject as well. So I'll talk about Reynolds transport theory. or what is popularly known as RTT. Okay, so is my screen clearly visible, by the way? Okay, great. So uh, can can any of you tell that, like, what is the control volume, what is the specialty? Let's say I have this. Okay, so let's say this is a control volume, CV. Okay, CV stands for control volume. So a control volume is a volume in space where you are giving your attention and interested to study the mass, momentum, and the energy which are either going or coming into the control volume, and what are the mass, momentum, and energy within the control volume. So there is a continuous influx and continuous efflux, and the continuous uh, influx and the continuous efflux across this control volume, and we are interested to know that what is that, like, we are keeping the attention on this fixed volume in space, and we are interested to know that how the quantities are changing across this control volume. Okay, so as I said, the control volumes is a just simply a region in space, okay, where you are interested to uh, studying things. So let's say in this way. So, and what is system? So the formulation, this Reynolds transport theorem, actually correlates, actually give a relation between a system and a control volume. So this control volume approach is particularly very important for the fluid mechanics and the thermodynamics viewpoint. But this system you all know, right? So all the equations, like let's say the Newton's law, uh, laws of thermodynamics, the basic heat transfers, these are all valid for a system. Okay, but in fluid mechanics problems or in thermodynamics problems, it is very often convenience to use the analysis across a control volume. So that's why how the formulations will go from a system to a control volume, that we want to know, and in that case it will helps us to directly use this use those formulations and solve different problems. Okay, so let's say that uh, this is my control volume at, let's say, time t equal to 0. Okay, or let's say at some time t. Okay, this is my control volume at time t. After some time, let's say delta t, my control volume is different. Okay, because there is a flow, and I am saying that the control volume may also move. Okay, so let's say after time t plus delta t, my control volume looks like this. Okay, so this is at time t plus delta t. Okay, and in a generic sense, let's say n is some property of the system. It may be mass, it may be energy, it may be momentum. Okay, it may be velocity. So property of the system I will represent it by n, which is an extensive property. And eta is equals to n by m, that is the property of the system per unit mass. Okay, I'm just defining it for my convenience. Okay, that eta is some quantity which is that actual property divided by the mass of the system. Okay, so this is eta. So now I will show different regions. So at time t plus delta t, this is my, so you can see that there are three regions in this case. Let's say this is my region 1, let's say this is my region, sorry, let's say this is my region 1. This, that means this black line and this blue line, these constitute the region 2. Let's say this is region 2, and let's say this portion which is hatched by these blue lines is region 3. Okay, now from the conservation principles, what you know, that the n, the quantity at time t was this blue line was at time t, right? So this I can write it as that n1 at time t plus n2 at time t. Now at time t I had the control volume which is this line. Okay, and within this portion I have only this region 1 and the region 2, nothing else. So am I right in saying this, that n at time t is equals to n1 at t plus n2 at t? Okay, so as I said, for the time being, let's say n is some property, and then I will show you that how you can use this to derive, like to directly get the continuity equations. Okay, and the also the momentum conservation equation, that is the Navier-Stokes equations in this case. So what is the quantity at time t plus delta t? So what is n at t plus delta t? What is that? So at t plus delta t I have only this region 2 and the region 3, so I can write n2 at t plus delta t sorry, plus n3 at t plus delta t. Am I right in this? And how you define the rate of change of, like we are interested to find that how this quantity looks like, dn by dt for the system, and we will see that this dn by dt, this is dn by dt will be an expression that will so in the right hand side of this expression will be the quantity which is going out of the control volume, like which will relate the quantity which is going out of the control volume going into the control volume, and which is there which like within the volume of the control volume, that will relate. Okay, so how is that dn dt? So this dn dt, or rather I should write it as delta n by delta t. So what is this delta n by delta t. How can I write it? So can I write it in this way, that this delta n is equals to n at time t plus delta t minus n at time t divided by delta t. This is the basic definition of this thing, right? This is the basic definition of derivatives. I am interested to find that how these dn by dt change, okay, and this is the basic definitions of the derivative, okay. Now if I take the limit, so limit delta t tends to 0, delta n by delta t is equals to dn by dt. Am I right? From the definition of derivative. So this system, can I write this now, that limit delta t tends to 0, this is n at time t plus delta t minus n at time t divided by delta t. Now what is n at time t plus delta t? From this is n at time t plus delta t. So that means that dn by dt, of course for the system, not for the control volume, is equals to what is n at t plus delta t. So n at t plus delta t is n2 at t plus delta t plus n3 at t plus delta t. Minus what is n at t? N at t was n1, so this is n1 at t minus this was n2 at t, n2 at t, okay, this whole divided by delta t. So I just substituted what is n at t plus delta t and n at t from these two expressions, from this and this, from this and this, I substituted those two in this expression, okay. So now fine. So this is my dn by dt. So what can I write from this? Okay, so here is a limit delta t tends to 0, definitely that is there. So can I write from this that this is limit delta t tends to 0, n2 at t plus delta t minus n2 at t divided by delta t plus limit delta t tends to 0, n3 at t divided by delta t minus, so I will write it within bracket, so this is n3 at t plus delta t minus this will be n3 at t plus delta t minus n1 at t divided by delta t, and this is within a big bracket, let's say. So what is this quantity? The first one from the derivatives, that some quantity is the n2 at region 2 at time t plus delta t minus n2 at region 2, like n at region 2 at time t by delta t. So from the definition, what can you say for this? That like n at region 2 for two different time scale, because this region 2 is the common region between time t and time t plus delta t. Okay, so this is the change at region 2. Okay, so this I can write it as dn by dt, simply delta n by delta t for the control volume. Okay, so this is delta n by delta t for the control volume, which I am writing as CV, plus what about this quantity, this n at region 3 at t plus delta t minus n at region 1 at t divided by delta t. So what does physically mean? This physically means that it is, so this limit delta t tends to 0, n at region 3 at time t plus delta t divided by delta t is, it's physically mean that rate of outflow. Okay, rate of outflow, sorry, yeah, so it is rate of outflow from the control volume. Okay, minus what is this n at region 1 at t, it is some sort of rate of inflow. So but I have not talked that the rate of outflow of what, that quantity is the n, that I don't know, that I will see later. Okay, so these things are rate of outflow minus rate of inflow across the surface of the control volume. Okay, so this rate of inflow and outflow, so at region 1 some quantity enters into the control volume at time t, which is across this surface. At time t plus delta t, some regions get out, which is that n at region 3, some regions like some quantity exited from the region 3, that is represented by this n3 t plus delta t divided by delta t. Okay, that is the rate at what the outflow is happening, and this is the rate at what the inflow is happening. So now let's say that I will now consider a control volume again. Okay, and let's say this is my some volume. Okay, some small volume within the control volume. Okay, let's say these I will represent by dV. Okay, V with a cut to represent the volume. So what is n? This capital N, can I write it in this way, that this is CV integral over the entire control volume into eta rho into dV, because this eta is the quantity per unit mass and this rho dV is the mass. Rho delta V is the mass of this small volume. Okay, rho delta V is the mass of the small volume. I am integrated the quantity eta across the entire volume. Okay, across this entire volume. So that n I can represent in this way. Okay, so this n is the integral across the control volume over this quantity eta rho into dV, where eta is equals to capital N by m, that is the mass of the system. But this mass of the system on the small control volume dm is the rho dV. Am I right? Okay, let me do it in different way. So what is dm here for this control volume? This dm is equal to rho dV, where rho is the density of the quantity and dV is the volume of the small volume dV. So what is then like d eta, or I can say that eta, like eta for this quantity. Okay, so this dn, like the quantity for this small volume, if I multiply this dm with eta and then integrate it over the entire volume, I will get the n. So n, I am integrating it across the control volume, and then eta rho into dv. Fine. In the similar way, I can express these two quantities, this n at region 3 at t plus delta t minus n at region 1 at t divided by delta t. Let's say I have a small control surface. Okay, so this is a control surface where I have the relative velocity between the control volume and the quantity. Let's say this is some v relative. Okay, and this relative velocity is between the fluid and the control volume, because always there is a influx and there is a outflux of the fluid. Okay, so this v relative is the relative velocity between the fluid and the control volume, because the control volume at time t was at this location, but at time t plus delta t it moves to this black, like the location has changed from this blue to the black one. So then the quantity which is because of this relative velocity or because of the flow will be what? So that one I can represent by this integral. So this will be integral over the CS. CS means is the control surface. Okay, so if I do the integral over the control surface of this quantity, eta rho is the density. Okay, and v relative dot n cap, where n cap is the normal at this point, outward normal vector, outward normal unit vector at this point, at some point on the control surface, into, let's say, this control surface, the area of that small control surface is dA. Now if I do this if I perform this integral, it will give me the rate of outflow minus rate of inflow. So this will give me the rate of outflow minus rate of inflow. Okay, so this rate of outflow minus rate of, this will give me the rate of outflow minus rate of inflow. By this integral I can represent the rate of outflow minus the rate of inflow. So what is the final equation which is coming? So dn dt for the system is equal to d capital dou n dou t. So it will be, let's write it in this way. So this will be dou n dou t for the control volume plus this integral over the control surface into eta rho v relative vector dot n cap into dA. Okay, so I can again write it in this way, that my dn by dt for the system will be equal to dou t of integral over CV, I will put the expression for n here. So what is n? N is integral. I will put the expression for n from there to here. So it is eta rho dv plus the same quantity. It is integral over control surface eta rho v relative dot n into dn, and this is the equation which is known as the Reynolds transport theorem. Okay, so this relates between the system and the control volume. So you can see it carefully that this left hand side represent the system. This left hand side quantity, that means this quantity, represent the system quantity, which is dn, that n might be mass, n might be momentum, n might be some energy, but the right hand side quantity are for the control volume. So this integral is performed over the control volume and this integral over the control surface. So these two relates between the system and the control volume. So let's, like in class, the professor derived the continuity equation, right? If I have not mistaken, the differential form of the continuity equation, that dou rho by dou t plus divergence of rho into v is equal to 0, that he derived in class. Let me derive that continuity equation from this RTT, Reynolds transport theorem. Okay, so this you have to keep in mind. Let's see how you can derive the continuity equation, that differential form of the continuity equation from this integral form. Okay, so this is basically the integral approach of solving problems in fluid mechanics. This is the through the Reynolds transport theorem. Okay, and you can solve a lot of problems using this formula, like using this formulation itself. So to demonstrate that how this integral approach relates with the differential approach, let me formally derive the continuity equation with which you are familiar from these equations itself. Okay, so let's say that I will derive the conservation of mass equation. Okay, so for this conservation of mass, what is the quantity I am talking about? M. So what is capital N? Capital N is equal to M. Am I right? Because I am interested about capital N, mass. So what is eta? Eta is equal to N by M, right? So eta equal to 1 in this case. For the conservation of mass case, eta equal to 1. So let me put it here. And what is the rate of change of mass? So what is this dn dt of system in this case? This is dn dt, like ddt of the mass of the system, and I am saying that I will derive the equation for the conservation of mass. So this quantity is 0 because the mass is conserved for the system. So this rate of change of mass with the time is 0. Okay, so it's from same equation you are deriving. Yes, I will derive the continuity equation which you properly known from this equation.